Welcome to today's paper reading. Today's paper is titled ShieldGemma, Generative AI Content Moderation Based on Gemma. This paper, titled ShieldGemma, Generative AI Content Moderation Based on Gemma, was published on the AR14 preprint by the ShieldGemma team from Google LLC. The paper introduces a comprehensive suite of LLM-based safety content moderation models, demonstrating superior performance compared to existing models and providing a valuable resource to the research community. The abstract introduces ShieldGemma, a suite of safety content moderation models based on large language models, LLMs, and built upon the Gemma 2 framework. These models are designed to predict safety risks across various harm types, including sexually explicit content, dangerous content, harassment, and hate speech, in both user input and LLM-generated output. The performance of ShieldGemma is highlighted by its superior results compared to existing models like Llama Guard and WildCard, with a notable 10.8% improvement in AU-PRC on public benchmarks. Additionally, the abstract mentions a novel LLM-based data curation pipeline, which is adaptable to a range of safety-related tasks and demonstrates strong generalization performance when trained on synthetic data. The release of ShieldGemma aims to provide a valuable resource to the research community, advancing LLM safety and supporting the development of more effective content moderation solutions. The widespread adoption of large language models, LLMs, has significantly transformed various fields, necessitating robust content moderation to ensure safe interactions. Current moderation tools, while providing initial safeguards, have limitations such as lack of granular harm predictions and fixed model sizes. To address these, this paper proposes a range of content moderation models with sizes from 2 billion to 27 billion parameters, tailored for different application needs. Additionally, a novel methodology for generating high-quality, adversarial, and fair datasets is introduced, reducing human annotation effort. This comprehensive framework aims to advance state-of-the-art in LLM-based content safety moderation, fostering safer interactions across various applications. The literature review highlights two main areas: safety content moderation and synthetic data generation. In content moderation, the focus has been on human-generated content within online platforms, with tools like Perspective API playing a significant role. However, the content within human prompts and LLM-generated responses presents a different challenge. Recent advancements in LLM content moderation include fine-tuning models such as Llama Guard and Aegis, as well as systems like MDJudge and HarmBench. On the other hand, synthetic data generation is crucial for developing robust safety models. Despite the abundance of human-computer interaction data, challenges such as scarcity of positive examples, limited adversarial data, and privacy concerns persist. LLMs, with their vast pre-training knowledge, have shown exceptional capabilities in knowledge demonstration and language understanding. Safety policies in AI systems are essential for defining guidelines that determine acceptable and unacceptable content. These policies provide a common framework for human annotators, ensuring consistency in labeling and reducing subjectivity. This alignment is crucial for training effective safety classifiers and mitigating biases in the data. By explicitly specifying what constitutes harmful or inappropriate content, these policies are instrumental in building zero-shot or few-shot classifiers, offering out-of-the-box solutions. The focus on user input is to prohibit requests that contain or seek to elicit harmful content, including those designed to manipulate the model. In contrast, the primary concern for model output is to prevent the generation of any harmful content, with user input serving merely as context. The content safety taxonomy provided by ShieldGemma defines 6 types of harm with detailed specifications. These definitions are further refined in the context of responsible AI usage. ShieldGemma is integrated into the Generative AI Toolkit by Google, released in 2024, focusing on synthetic data curation. This integration is crucial for AI-driven content moderation, aiming to prevent harmful content through advanced safety measures. The synthetic data curation process involves several key policies to ensure the content's appropriateness. These include restrictions on sexually explicit information, hate speech, and dangerous content. Additional restrictions cover harassment, violence, and obscenity or profanity. The data is generated using a synthetic pipeline, which employs active learning to minimize human annotation. This approach allows for the creation of diverse, adversarial data. Post-annotation, the data is augmented to include diverse categories such as gender, ethnic groups, sexual orientation, and religion, enhancing the fairness of the models. The generated data is used for both user input and model response scenarios, ensuring compliance with the established policies. The raw data curation process begins with problem definition, where the scope is limited to specific harm types such as hate, dangerous, sexual, or harassment, and the language is restricted to English. The Gemini LLM is used to generate a list of generative AI use cases. Next, query generation involves using an instruction-tuned LLM to create diverse adversarial prompts based on parameters like harm type, topic, use case, and locale. Finally, data expansion results in the generation of 50,000 user input examples and 50,000 model responses, evenly distributed across various use cases and topics. This ensures a comprehensive dataset for further analysis and testing. Figure 1 illustrates the synthetic data generation pipeline used in the ShieldGemma project. This pipeline leverages large language models, LLMs, to create diverse and adversarial datasets for training safety content moderation models. The process involves generating synthetic data that covers various dimensions such as length, targeted harm types, and sensitive topics. Active learning techniques are employed to minimize the need for human annotation, thereby enhancing the efficiency and scalability of the data curation process. The pipeline ensures that the synthetic data is both diverse and challenging, which is crucial for training robust and fair safety models. In this section, the authors discuss the expansion of raw data along dimensions such as difficulty and diversity using a self-critiquing and generation framework. For semantic and syntactic diversity, they generated 5K examples, and for difficulty, another 5K examples were created. This process resulted in a total of 20K expanded examples. The expanded data was then combined with 100K synthetic raw data and 14K anthropic HHRLHF data to form the final dataset. To further enhance diversity, the authors subsampled the anthropic HHRLHF data, keeping the first utterance for 50% of the data to mimic user input, and the first prompt response pair for the remaining 50% to mimic model response. The purpose of data subsampling is to streamline the annotation process by reducing the amount of data that needs to be annotated, thereby speeding up the iterative process and minimizing examples that the base model can confidently predict. To achieve this, the authors employ the cluster margin algorithm, which is recognized for its state-of-the-art performance and scalability to large datasets. This algorithm aims to balance the uncertainty and diversity in the subsampling process. The process involves generating BERT embeddings for the entire dataset, clustering these embeddings using agglomerative clustering, and then selecting examples with the smallest margin scores. A round-robin method is applied to further downsample the data to the desired batch size. This iterative approach allows for continuous improvement of the model. In the data annotation process, the authors employ 3 raters to evaluate and rate the data. The final label is determined through a majority vote. For model responses, raters assess whether the response violates policy based on the user input context. The test data includes 2,671 benign examples and a variety of adversarial examples categorized by harm type, such as hate, dangerous, sexual, and harassment. Additionally, there are 40 examples of obscenity and 70 examples of violence. Although the model is trained on all 6 harms, performance is reported only on the 4 targeted harms. The presence of 141 examples annotated with multiple harms adds complexity to harm type level prediction. To enhance the fairness of the model, the authors employ counterfactual fairness expansion techniques, referencing methods from Kussner et al. 2017 and Smith et al. 2022. This involves expanding the training data across various identity categories such as gender, race, ethnicity, sexual orientation, and religion. The process begins with a large language model, LLM, identifying related terms like male for gender or Japanese for ethnicity. If such terms are found, another term within the same identity category is randomly generated, and a few-shot LLM is tasked with replacing the original term while maintaining the same meaning and correct grammar. The expanded data then undergoes a human audit to filter out any inappropriate examples, after which the original label is treated as the ground truth for the newly generated data. Finally, the model is fine-tuned using this expanded and audited dataset to improve fairness. In this section, the authors describe the process of supervised fine-tuning, SFT, for Gemma 2 instruction-tuned, IT models, which include models with 2 billion, 9 billion, and 27 billion parameters. The models are fine-tuned using specific instructions and produce binary outputs, either yes or no. The training setup involves using TPV5 Lite with a batch size of 16, a maximum sequence length of 8,000, and a learning rate of 1 × 10 to the power of -6. The models are trained for 4,000 steps, and the best checkpoints are chosen based on validation data. The predicted probability is calculated using a formula that includes log likelihoods of the generated tokens, temperature, and an uncertainty estimate hyperparameter. To address the challenges in comparing safety-related datasets, the authors conducted experiments in binary and harm type level classifications. For binary classification, they aggregated prediction results into binary outcomes by maximizing probabilities over all harms, reporting both optimal F1 and AU-PRC scores for models providing probabilities, and F1 scores for those with only binary results. In harm type level classification, they provided a detailed performance comparison using a 1 versus all setup. The benchmark results show that all ShieldGemma (SG) models outperformed baseline models, with SG9B achieving a 10.8% higher average AU-PRC compared to Llama Guard 1 on external benchmarks, and its F1 score exceeding that of WildCard and GPT-4 by 4.3% and 6.4%, respectively. Table 1 presents the evaluation results of various models based on optimal F1 and AU-PRC metrics, with higher values indicating better performance. The evaluation uses alpha equals 0 and equals 1 for probability calculations. ShieldGemma's 9B and 27B models show the best performance on both internal and external benchmarks, which include OpenAI moderation and toxic chat datasets. The performance of baseline models on external datasets is sourced from Ghosh et al., 2024, and Anand et al., 2023. Figure 2 illustrates the instructions for supervised fine-tuning in 2 scenarios, user input and model output. On the left, it details the process for evaluating whether a user prompt violates safety policies, focusing on no hate speech. On the right, it outlines the steps for assessing if a model's response to a prompt breaches these policies. Both sections emphasize starting the answer with yes or no and then providing a detailed justification. This figure is crucial for understanding how the fine-tuning process ensures the model adheres to safety principles. The authors acknowledge several limitations in their model. Firstly, in terms of fairness, despite implementing counterfactual expansion to mitigate bias, label discrepancies may still occur when identity groups are swapped, often due to inherent biases in the pre-training dataset. Secondly, regarding generalization, larger models show stronger performance on external benchmarks with new harm types and text styles, but additional experiments are needed to verify this on other datasets. Lastly, the model's interpretation of policy violations may be overly conservative, potentially interfering with helpfulness. The authors recommend that downstream clients adjust filtering thresholds based on their specific use cases. Figure 3 illustrates the harm type level performance, measured by AU-PRC, for the SG prompt and SG response datasets. Notably, all ShieldGemma (SG) models significantly outperform GPT-4 across various harm types. Specifically, SG9B and SG27B models show slightly higher AU-PRC compared to the SG2B model, indicating stronger generalization capabilities. Conversely, GPT-4 struggles to differentiate between different harm types, as evidenced by misclassifications such as 76% of hate speech data points being classified as positive for harassment. This paper introduces a significant advancement in safety content moderation through a suite of specialized models built on the Gemma 2 language models. These models demonstrate superior performance across diverse benchmarks, underscoring the effectiveness of the approach. Additionally, the novel synthetic data generation pipeline provides a valuable tool for creating high-quality, diverse datasets, which is beneficial for both safety and other research domains. The authors are enthusiastic about sharing these resources with the research community to further develop this critical area. In this section, we acknowledge the significant contributions of core team members such as Wenjun Zeng, Yuchi Liu, and Ryan Mullins. Additionally, we recognize the support from various specialty areas including central support, checkpoint conversions, and ethics and safety. The work is also made possible by the dedicated efforts of teams at Google, particularly the Gemma, Google DeepMind Responsibility, and Kaggle teams. Thank you for watching.